In the last notes, we did confidence intervals for the difference in proportions. In these notes, we're going to do some significance testing for difference in proportions. So the first part here says, what are the conditions for conducting a two-sample z-test for difference in proportions? And remember, that's P1 minus P2. And these are actually going to be the same as the conditions we use for confidence intervals for P1 minus P2. So we know the data come from either a random sample or a randomized experiment. We have the independence condition. Don't forget, if you're sampling without replacement, we use the 10% condition to meet that criteria. And for normality, we just make sure we have at least 10 successes and 10 failures for each sample. So those are actually the exact same as the conditions for a confidence interval for P1 minus P2. So what are the hypotheses going to look like for our significance test? Well, remember the null hypothesis. No matter what test you're doing, it's a statement of no difference. Things are the same. So if P1 and P2 are the same, right, then if we did P1 minus P2, it would be equal to 0. So the null is always no difference. Or another way you could write that, if you prefer, you could just say P1 equals P2, right? Just add P2 to both sides. P1 equals P2. So that's what our null hypotheses will look like. So the next part here says, what's the standard error that we're going to use? And then what's this pooled sample proportion, and why do we pool the sample proportions? So I'm actually going to start there. So we have this thing called a pooled, or you could call it a combined sample proportion. So when you think of pooling things, like if we pool our money, that means we put all our money in one group together, right? So maybe we can make a bigger purchase or something. So in this case, instead of P1 or P2, we're going to put a little c down here for combined. And the formula is this: x1 plus x2. So that's the total number of successes from each one. So the first sample, number of successes, second sample, number of successes, over the total sample size. So now we have a combined sample size in the denominator. Okay, so I said if we pool our money together, we can make a bigger and better purchase, right? So the idea of pooling proportions together is so we can have better data. So why would you pool these things together? Total successes over the total sample size for each. Well, we start out in significance tests by assuming that the null is true, right? So we're going to assume really that P1 and P2 are the same. So if P1 and P2 are really the same, that's what we start out by believing. Then if we pool the two samples together, that actually gives us better data by giving us a bigger group, right? Like pooling our money together. Now we have more money. So it's like we have a larger sample now, right? So we have better data in a sense. And to be clear, this is only for a test, right? A two-sample z-test for a difference in proportions. It's only for when we're doing a test. We don't start out making our confidence interval assuming that they're the same. But in hypothesis testing, we start out by making that assumption. So we're assuming that P1 equals P2. So pooling our data, in a way, gives us better data. Okay, so the standard error, you'll recognize it. It's the big square root. And everything is the same except for now for all the p-hats, we just use the pool proportion. This one's still over N1. This one's still over N2. So the square root should look familiar. Just remember, when we're doing hypothesis testing, that's when we use the pool proportion, because we make this assumption that they're the same. All right, and then we're going to use this standard error piece when we go to the next part of the notes here. It says, what's the test statistic for these two sample z-tests for the difference in proportions? Is it on the formula sheet? You probably already know the answer to that one. And what does the test statistic actually measure? So, a test statistic for proportions, it's always a z-score. right? It's a z-score. We start by taking our sample data, so the difference in the P1 sample minus the difference in the P2 sample, or the proportions in each, rather. And then we compare that to the null hypothesis, which we said earlier that was 0. And then we divide by the standard deviation. So now we have this pooled thing for our standard deviation down here. And the 0, just a reminder, that came from the null hypothesis, right? The null hypothesis said P1 minus P2 equals 0. We start out by assuming that's true. So that's our test statistic. No, it's not on the formula sheet. The formula sheet says something really general, like sample statistic minus population parameter divided by standard deviation of statistic, right? It says something really general. So no, this one, the way it's written, is not on the formula sheet. So what does it measure in blue? What does the z-score actually measure? Well, it does still sort of measure standard deviations, right? But now it says how many standard deviations our sample difference, right, p hat 1 minus p hat 2, is from the null hypothesis, which that value is 0. So this z-score measures how many standard deviations our sample difference is away from the null hypothesis value, which was 0. Okay, and we're going to need our test statistic formula here because we're going to do an actual example of a significance test in the next part here. So example 1 is about hearing loss. It says, are teenagers going deaf? In a study of 3,000 randomly selected teenagers, which ran from 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers that just ran from 05 to 06, 19.5% showed some hearing loss. This is actual data reported in the Arizona Daily Star in 2010. So some skeptic might say, wow, teenagers used to not lose as much hearing as they do now, right? Teenagers nowadays are losing more and more hearing. And I say nowadays like this isn't over 10 years ago, but I was a teenager then, so 05 and 06 are still teenage years in my head. Anyway, the question here in Part A, did these data give convincing evidence that the proportion of all teens with hearing loss has actually increased? Or was this some sort of chance variation, right? Maybe they're roughly the same, it's just you had a random sample that showed only 15%, and then there was another random sample that showed 19.5%. So is that convincing evidence, or was that just some chance variation? So the convincing evidence piece, that's your clue that we should really run a significance test. So it's a 4-part grading rubric. Let's start with the state step. So we want to test 2 hypotheses. The null, this one's going to be pretty much the same every time, is going to say that those 2 proportions, the true population proportion of teenagers from that generation and from that generation, are actually the same, right? So P1 minus 2 would be 0. That's the null hypothesis. Then the alternative would be, we're trying to suggest that one of them is actually bigger, right? We're trying to say that this group of teenagers actually shows more hearing loss than the older group of teenagers. So let's just be clear about which group is P1 and which group is P2. So when we define those parameters, we can say where P1 and P2 are the true population proportions of teens showing hearing loss in 05 and 06 and 88 to 94 respectively. So 05, 06, that group would be P1, and the 88 to 94, that group would be P2. Ooh, don't forget to mention an alpha level. I'll just use the default, right? We'll use alpha equals 0.05 for our test. That's what we're going to compare our p-value to when we get done. Okay, so for the plan step, the first point we can get right here is let's name the test that we're going to run. So we can say it's a 2-proportion z-test for P1 minus P2, right? The true difference in these proportions. So there's one thing the AP graders will look for. Do we actually name the test, or the confidence interval if we were going to make one? Do we actually name it? And And then for the conditions, the randomness condition, it says the teenagers were randomly selected. So randomness is good. As far as independence goes, even though they sampled without replacement, right, we should be well below 10%. So both sample sizes, whether it was the 1,800 from this group or the 3,000 from that group, they're both well below 10% of all teenagers. So the 10% condition is met. For normality, this one gets a little bit tedious, but the math's really simple behind it, right? 10 successes and 10 failures for each sample. So let's start with N1, P hat 1. Right, so 1,800 was the sample size. It was 19.5% that showed hearing loss, so 0.195 times 1,800 gives us 351, which is definitely at least 10, so we're good there. And then let's do N1, 1 minus P hat 1. So 1,800 times, how did I get 0.805? We'll just do 1 minus 0.195, right? So the remaining number of teenagers from that group would be 1,449, which is also at least 10. So check mark there. So sample 1 is all good. How about sample 2? N2, P hat 2. So 3,000 minus, or rather times 0.15 for the 15%, which is 450. Definitely bigger than 10. That gets a check mark. And then N2, 1 minus P hat 2. So 3,000 for the sample size. 1 minus 0.15, that's 0.85. So that's at 2550, which is also at least 10. Trust me, I wouldn't go through and show those if I didn't have to, but that's a requirement for the AP exam. So if you're going to meet this condition, right, we can say because all of these are at least 10, the large counts condition is met. And we have to show each calculation. All right, so now we're on to the do step. We need two things in the do step. We need a test statistic and we need a p-value. So our test statistic with proportions, we talked about it a little while ago. That's a z-score. We subtract the sample data, p hat 1 minus p hat 2, compare it to the null hypothesis, which is just 0. And then we have that square root thing, but now we have these pooled proportions in our standard deviation. So that little c, remember that stands for combined, right? Those are our pooled proportions. And that's unique to these two proportion z tests because we start out by assuming that P1 equals P2, right? So that doesn't happen for confidence intervals. It only happens in these types of tests for proportions. Okay, so to be able to actually calculate this test statistic, this z-score, we need this p hat sub c. We need this pooled proportion. So let's start with the total number of successes. And we already calculated that in the normality condition, right? There was 351 for the first sample and 450 for the second sample. Over the total sample size for each one, which is 1,800 plus 3,000, which gives us 801 divided by 4,800. So our pool proportion would be approximately 0.167. So if we pool those two samples together, we're really looking at 801 for the number of successes out of a total of 4,800. So bigger sample, better data. All right, so let's get this z-score. P hat 1 minus P hat 2. So that was the 19.5% minus the 15%, minus 0. And then the square root, we've got our two sample sizes, N1, N2. And then let's use the pooled proportion and then 1 minus that pooled proportion here and here. So definitely be careful when you're plugging this into your calculator. You should be at about 4.05 for the z-score if I rounded 2 decimal places. So we've got the test statistic. Our z-score is 4.05. Now let's use that to get the p-value. So the p-value, in other words, is saying what's the probability you would get a z-score that huge, right? We're going to try to shade the tail, everything above 4.05 standard deviation. So if I can illustrate that in a normal curve here, this is just the standard normal curve where the z-scores come from. So the mean is 0, the standard deviation is 1. And if I go 4 standard deviations down the line, here's 4.05, this tiny little bit at the end of this tail. So you could use normal CDF, you could try to use the normal chart. I want to show you what the 2-prop z-test command does in the calculator. So if I go to stat and then over to tests, the 6th one down is 2-prop z-test. 2-prop z-test. So x1 and n1, you've got to use integers, right? Number of successes over the total for the first sample, and then number of successes over the total for the second sample. And then this line asks about our alternative hypothesis, which we said P1 is greater than P2, right? So this sign, the direction of it, greater than, should always match the sign from our alternative hypothesis. So if our alternative hypothesis was P1 minus P2 is greater than 0, look, the sign should match, because another way to say this would just be, if we add P2 to both sides, P1 is greater than P2. All right, so I'm going to hit calculate here. And I've got a few different values. This is the z-score, 4.047. If you quickly glance at the p-value, p, it might not make sense to you. I thought probability was supposed to be a number between 0 and 1. So I still have kids that will legitimately write 2.58 as the p-value. Please do not make that mistake. If you look closely, it says e to the negative 5. So in other words, that means move the decimal place out 5 spots. 1, 2, 3, 4, 5. So that means there'd be 4 zeros in front of this 2. So this p-value is actually trying to communicate to you a really, really small number. So keep that in mind. The p-value has to be a number between 0 and 1. If you get something funny like that, it's probably because it says e to the negative 5 or something like that at the end. Okay, so there's our test statistic z. There's our p-value. That's p hat 1. That's p hat 2. And then I guess the p hat with nothing on it, that should look familiar. That would be our pool proportion. All right, so we've already got those. Let's take this p-value back to the do step. So that little tiny space right there represents our p-value, which was 0.0000, 4 zeros, 2584. In other words, if there was really no difference between that generation of teenagers and that generation of teenagers, it's almost an impossible chance for us to see a difference this big in the hearing loss. So for the conclude step, we can say because our p-value, which is really small, that's less than alpha equal to 0.05, we're going to reject the null hypothesis. That's very convincing. Definitely statistically significant. And then to put that in context, we have convincing evidence, basically of this statement right here, what they asked for, right? We have convincing evidence, I'm going to use their words, that the proportion of all teens with hearing loss has increased. So my generation definitely showed more hearing loss than this generation. And we're making inferences to represent all the teenagers from my generation as compared to all the teenagers from this generation, just based off these 2 samples. All right, so part B says between the 2 studies, Apple introduced the iPod. Right, so that was a big thing between those 2 generations that occurred. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? Can we just point to iPods and say, you know what, that was it? And the answer is definitely no, right? Although we know for sure that there was an increase in hearing loss, we can't just blame iPods because we'd have to conduct a randomized experiment, right? Before we can say something caused something, before we can establish causation, we'd have to conduct a randomized experience where we randomly assign some kids to listen to iPods and some not to listen to iPods, and we see if they have any hearing loss. Now, That's not ethical either, right? But we certainly can't say, just from looking at our data, that iPods caused the hearing loss. We can speculate to some degree, but we definitely can't establish causation. So we cannot conclude that iPods are the cause. I mean, there could be other causes, right? Other factors, such as car stereos or concerts, that would also play a role. So that would confound our data, right? That's why we'd have to establish causation with an experiment that has some control, that ruled out car stereos and concerts. All right, and the last little bit here. Is it okay to use a calculator? Yeah, please do. There's a lot to mess up with entering the square root and all the algebra, so just use your calculator. It's stat, test, 2-prop, z-test, 2-proportion, z-test. Are there any drawbacks? Just be sure that you label the inputs and outputs, right? Make sure you do that correctly. And by the way, if you try to use decimals instead of integers, you'll get an error. So make sure you use integers, like number of successes out of the total. All right, so now we've done tests of significance for difference in 2 proportions, P1 minus P2. We learned about pooled proportions, which is only for tests of significance. And we learned a new calculator command. So that is all for these notes. I'll see you in class.